Hello and welcome to another of my chemistry videos. Today we're going to talk about significant digits, and we have listed all the technical information, the state content standard and the objective. You as a student will provide the correct number of significant figures in a given calculation. Alright, so let's get on with it. Significant digits, rules and practice. And why this matters is probably important to cover right up front. In chemistry, we often deal with very small measurements. Variations can occur from one measurement to the next. You may not have ever seen significant digits in a math class before because in math, we're really dealing with raw numbers and a bit more abstract calculations. In chemistry, all the calculations we do, I will go out and I'll say all the calculations we do are really measurements. And significant digits have to do with the accuracy of the equipment that was used to make those measurements. But first we need to talk about a couple of definitions relating to that equipment. Often the terms precision and accuracy are used, you can use one or the other in most of the world, and they interchangeably. That's the word I'm looking for. But in science, precision is a measure of how close individual measurements agree with one another, how repeatable they are. Now, let's say, for example, I were to step on a scale, and each time I step on a scale, the scale tells me that I weigh 507 pounds, and I step off and I step on again, 507 pounds each time. Well, that's a very precise scale. It's not very accurate, I can tell you. I don't weigh 507 pounds or even anywhere close to that. But this piece of equipment, this scale, would be very precise if it keeps coming up with that same number. And you look at the picture here, maybe this graphic helps. If you're playing darts and you keep hitting pretty much the same spot, it doesn't have to be in the middle. It's not in the middle. It's off to the edge somewhere, and you keep hitting the same spot. That's very precise. You're a very precise dart player. Now, let's look at accuracy. Accuracy refers how close individual measurements agree with the correct or true value. Let's go back to that scale again. Let's say that scale I got on says I weigh 507 pounds. I know I don't weigh that much. So I calibrate the scale. And now when I get on that scale, it's really close to what I actually weigh. And if it's right on the true value, that's an accurate scale. Now, I could get something like this picture here, playing darts. I mean, every time it hits, you play darts, you hit a bullseye. That's very accurate. And your shots playing darts are also grouped very closely, so it's also very precise. So this graphic here illustrates both accuracy and precision. Now, if I were shooting darts and I hit one dart right in the middle, and I hit another dart maybe like over here, and another one was over here, or one off to the edge. Now, I had one shot that was accurate, but if my shots are all over the board, that's not precise. So I could have an accurate one, but other ones not so accurate and not so precise. Make sense? Okay. Uncertainty in measurement. Measured quantities are generally reported in a way that only the last digit is uncertain. Now if we look at our pictures here again, we have a picture of a thermometer. And this thermometer, it has our tens. We've got 60 degrees, 70 degrees, and it's got some marks in between. It looks like every couple of degrees there's a mark. So we got 62, 64, about 66 degrees. But how certain are we? I mean, maybe it's 65 degrees, maybe it's 67 degrees. So can you see that there's just a little bit of uncertainty here as to just how accurate or how close to the true value this thermometer is. Again, over here, we can have the same thing measuring a pencil. Maybe this is millimeters. Maybe it's 8.4 millimeters. Maybe it's 8.5. Maybe it's 8.3. There's always just a little bit of uncertainty. No matter how much you zoom in, there will always be some uncertainty. There's always one digit that's uncertain. Another example here with clocks. If you wake up in the morning, you see it's 4:12, which nobody would like to see, 4:12 in the morning, alarm going off. But you don't know 4:12 and how many seconds. Maybe it just turned 4:12. Maybe it's about to turn to 4:13, so we could have 55 seconds here. We could have 4:12 and 2 seconds. So there's a little uncertainty. Significant digits are all digits of a measured quantity, including the uncertain one, that last one we don't know about. Okay, now here we have a case where probably be the only time you'll ever see this in your life. Homer Simpson is more accurate than a digital clock. This Homer Simpson clock has a seconds hand on it, so it's more accurate. It can get closer to the true value than what this digital clock can. But even there, we have some uncertainty. Now we've got seconds. Now what about tenths of a second? So I think you kind of get where we're going with this uncertainty thing. Okay, first thing we'll need to know about significant digits is how to count them. And just like when you're reading, you start from the left and you work to the right, and the first significant figure is found by going from left to right, and it starts with the first non-zero digit. So our first example here, we've got some zeros up front. They aren't counting. Okay, right here is our first non-zero digit. It's a 3. So here the 3 is the first significant digit. Here we have 1 0 on the front. We hit a non-zero digit going over to the right. This 4 is the first significant digit. Here, very first one we hit, the 7 non-zero digit, that's our first significant digit. Okay, there are 0 rules that you're going to need to be aware of. There's actually 3 of them. And here we have the first 0 rule. Zeros at the beginning of a number are never significant. They just indicate the position of the decimal. Now, don't get confused. We do need those zeros to recognize what the value of our number is. But as far as significant numbers, zeros at the beginning are not considered significant. So here, in our first example, zeros at the beginning doesn't count. Oh, here's one, non-zero number, 1 significant digit. And here in our second example, zeros at the beginning don't count. Okay, here's a significant digit, but now we have another one after it. So here we have 2 significant digits. Okay, we'll come back to these later, but we have 2 more rules to cover. Another 0 rule. Zeros between non-zero digits are always significant. So we're going along in our first example. This one is significant because it's not a 0. A couple of zeros and another one here significant because it's non-zero. These zeros are in between the 1 and the 5, therefore they are significant. So here we have 4 significant digits. Okay, second example. We have a 5, obviously significant because it is not a 0. A 0, a 6. Okay, we've got a 0 in between them, so that counts as significant. So we've got 1, 2, 3 significant digits, another 0, which counts because it's between the 6 and the 0. So you get to counting, and here's another 0, which is also significant because it's between 2 non-zero numbers. So all of these digits, all 9 of them, are significant digits. Let's move on to our third and final 0 rule. Zeros at the end of a number are significant if the number contains a decimal. If there's no decimal, zeros at the end do not count. So here we have zeros at the beginning. Remember our first rule, zeros at the beginning, never significant. Here's our first significant digit, a 2. Okay, we've got 2 zeros at the end. So we look back, we have a decimal, so these count. So we've got 1, 2, 3 significant digits. Second example, here's a 3, which is significant. We've got a decimal, so this 0 also counts at the end, 2 significant digits. Okay, here we have a 7, which is significant. We have 2 zeros but no decimal, so these zeros at the end do not count as significant. Whatever measured this is only accurate to the hundreds place. These zeros are just here as placeholders. So anyway, 1 significant digit. Now this one right below it has a decimal, 700, but with a decimal at the end, indicating that whatever measured this is not only accurate to just the hundreds, it's also accurate to the tens and the ones place. So hopefully this here helps you understand what that decimal is telling you about what measured it and the accuracy of that equipment. That's our zero rules. So here, you get a chance to practice. If you need to, go ahead and stop the video and write down what you feel would be the correct answer for each of these just by looking at the zero rules. And I'm going to just uncover them here one at a time. Remember, we got a zero rule about zeros in between, so 4 significant digits, zeros in between count. This one here, every one of these numbers is something other than 0, so they all count, 4 significant digits. This here has 2 rules that apply. Zeros at the beginning, never significant. If there's a decimal, zeros at the end are significant. Therefore, we have 4 significant digits. 1, 2, 3, 4. Okay, here again. 1, 2 zeros at the beginning, they're not significant. Here's our first significant digit. But we do have 1, 2, 3 significant digits. Here we have zeros in between non-zero numbers, so they are significant. So all of these digits are significant. So we have 6. Here we have a 0 in between non-zero numbers, so this one counts. We have zeros at the end, but no decimals, so these don't count. So when we're talking about terabytes, we have 3 significant digits. All right, let's move on. Scientific notation and significant digits. This may look complicated, but it's really not. It's just as simple as ignoring the tens and the exponent, and then you just follow the rules you were already given. So if I were to ignore this, just looking at this part right here, I have a 0 between non-zero numbers, so 3 significant digits. Here we have the 0 in between, it counts. We've got a 0 at the end and a decimal, so all 4 of these count. Here we have a 0 between non-zero numbers and 2 zeros at the end and a decimal, so we have 5 significant digits. Does this kind of make sense? Sometimes if you're asked to write a number with using a certain number of significant digits, it may be easier to put the answer in scientific notation. Again, you still need this part because it does indicate the value of the number overall, but how accurate the piece of equipment was is indicated by the significant digits. Okay, moving on. Significant digits in calculations. We're going to talk about adding and subtracting here. The answer will have the same number of decimal places as the measurement with the least number of decimal places. So if I add these together the way I normally would, just punch them in your calculator, scratch them out on a piece of paper, you add those together, you're going to get 104.842. Now, this is where we can do this the way we always do and then deal with this rule. Now we look at the number of decimal places. Which measurement, this one has 2 decimal places, which measurement has the least number of decimal places? This has 3. This here only has 1. Therefore, our answer has to be rounded to have 3 decimal places. So I'm going to round it off. This is a 4, so I drop off the 4 to 104.8. Simple enough, right? Now, don't get it confused with this next one. Multiplication and division. The answer is rounded to the same number of significant digits as the measurement with the least number of significant digits. This has nothing to do with decimal places. Multiplying and dividing is the same number of significant digits. So again, you multiply just like you normally would. Punch that in your calculator or on a piece of scratch paper, and you come up with 32.3492 centimeters squared. Or centimeters times centimeters is centimeters squared. Now we look at our rule. Which measurement had the least number of significant digits? Here we have 4 digits. Here we only have 2, which means our answer gets rounded to have only 2 significant digits. So we're going to get rid of all of this, round it down to 32 centimeters squared. Your turn. If you need to, go ahead and stop the video here and calculate this yourself. Again, multiply them together the way you normally would. We're calculating the volume of a box. Here's the lengths of all 3 sides. You multiply all those together, and you're going to come up with 2,285.01 centimeters cubed. Okay, and now you look at your rule for significant digits when you're multiplying. and you're going to round your answer to match whichever of these has the least number of significant digits, which is right here, 2. So you could put your answer in scientific notation like this. Another possibility is to write 2,300. Remember, no decimal at the end, and the zeros at the end don't count. So there's 2 ways to write that answer, either one equally correct. More practice. It takes a runner 10.5 seconds to sprint 100 meters. So calculate the average speed of the sprinter in meters per second, and then use correct significant figures. Okay, so meters per second. So we've got meters divided by seconds, and then when you get your answer, then look at your rule for correct number of significant digits. Here we have 3, 4, 5 significant digits. Here we only have 3. So our answer is right here, 9.52 meters per second. Okay, well, I hope this helps you understand significant digits a little bit better. At our level, we will not see multiplication and addition in the same equation. We'll leave that for the college folks. Leave that for when you get there. Hope this helps you understand it. See you next time.